Recurrent neural networks process sequence data one step at a time, evaluating each token in a fixed order. This architecture creates a mechanical bottleneck, preventing the parallel computation capabilities of modern GPUs from being fully utilized. Because each step relies on the output of the previous one, processing long sequences forces data through deep, cyclical pathways. This triggers severe gradient degradation, capping the model's memory limits. On the left, the RNN evaluates a sequence step by step, with information decaying. On the right, the transformer processes an entire sequence matrix simultaneously. Through parallel matrix multiplication, it achieves an O of 1 path length. Every piece of data connects in a single step. To understand how this works in practice, we will trace the exact mathematical life cycle of a sequence as it passes through the scaled dot product attention mechanism. This architecture moves towards a mathematical structure designed specifically for tensor core parallelism, intentionally removing the need for sequential logic loops. The process begins with a raw sequence of input vector embeddings. Each token is initially represented as a dense array of numbers. To route information dynamically, the model projects this single input into 3 distinct functional roles: a query, a key, and a value. The input matrix multiplies against 3 learned weight matrices, generating 3 new functional matrices. The query matrix represents what a token looks for. The key matrix is a semantic index. The value matrix holds the raw data payload. Because Q, K, and V are linear projections of the exact same input tensor, the network queries its own data. This defines self-attention. The first step of the attention equation computes the interaction between the queries and the keys via the QK transpose dot product. The key matrix must be transposed to mathematically align the inner dimensions, allowing it to be multiplied against the query matrix. The query matrix multiplies against the transposed key matrix. A single row and column interact to produce one scalar cell. This dot product calculates geometric similarity. Large positive values mean vectors are aligned and relevant. Near zero values indicate they are orthogonal and irrelevant. The abstract concept of attention is practically executed as a pure geometric calculation. It measures spatial similarity between high-dimensional vectors. This QK transpose matrix introduces a mathematical danger. As the vector dimension, dk, grows larger, the magnitude of the resulting dot products grows exponentially. These massive dot product values push the subsequent softmax function into extreme, flat regions where gradients approach absolute zero. Raw, unscaled dot product values spread extremely wide into shaded zero gradient zones. To correct this, we divide the matrix by the square root of dk. This scaling instantly compresses the variance to 1, centering the data safely. This stabilization ensures healthy, active gradient flow during backpropagation, allowing the neural network to continuously update its weights and learn. Dividing by the square root of dk is a mandatory stabilizer, required to push matrix operations to industrial scales without stalling the training process. With the matrix stabilized, the network applies a softmax function across each row of the scaled n by n matrix. Softmax converts the raw geometric similarities into a normalized probability distribution. Every weight in a given row now sums to exactly 1. The final operation in the equation multiplies this n by n probability matrix against the n by dk value matrix phi. The attention weight matrix multiplies against the value matrix. A single row of the output is computed as a weighted sum of all vectors in V, pulling numerical payloads only from highly aligned tokens. This final mathematical output yields a context-aware blend of the entire sequence, achieved simultaneously in one operation. A single set of Q, K, and V projections restricts the model to viewing the sequence through a single learned perspective. Language and complex data require tracking multiple relationships at once. A model must map syntax in one mathematical space, while mapping semantics or sentiment in another. This graphic demonstrates the multi-head attention architecture. The completed scaled dot product calculation block shrinks and duplicates H times side by side in a parallel array. Instead of one pass, the architecture runs H independent sets of query, key, and value weight projections entirely in parallel. The outputs from all H heads concatenate back together into a single matrix. This combined matrix passes through a final linear weight layer, WO, to restore the original D-model dimensions. Multi-head attention allows the network to process drastically different representation subspaces simultaneously. This exponentially increases learning capacity without adding sequential processing time. This journey bypassed the traditional sequence bottleneck by transforming continuous data processing into discrete differentiable retrieval. The maximum mathematical path length between any two distant concepts in a sequence is now reduced to O of 1. These massive, uninterrupted matrix multiplications map precisely to the physical grid layout of modern GPU tensor cores, ensuring maximum hardware utilization. Attention is a highly parallelizable geometric weighting function. By engineering a mathematical structure that aligns with physical compute hardware, this mechanism solved the deep learning scaling bottleneck and provided the mathematical basis for modern generative AI.